I'm Bob McPherson, and this brief video is a summary of my final project for Big Data Analytics through the Harvard Extension School. The topic of my project is Forensic Server Log Analysis with Hive and MapReduce. Server security and data breaches are increasingly in the news. Forensic analysis of server logs is necessary to identify vulnerabilities, perform damage assessments, prescribe mitigative measures, and collect evidence. Massive collections of server log data are difficult to analyze with conventional means. Hadoop, MapReduce, and Hive software provide a solution. HiveQL and HQL queries assist in performing forensic analysis, and Hive can produce analytical data sets for other software tools such as R and Mount. Methods of analysis include performing fuzzy searches for keywords and terms, time aggregations of weblog variables for trending, performing sorting to identify potential problem sources, creating analytical data sets suitable for further analysis. Data needed to run this analysis are located at the URL provided here. You can pause and you can jot that URL down if you're interested in going and downloading a copy for yourselves. But the data consists of 6 Apache server logs from Amazon's sample collection. There's a 7th log which I added that includes known security breaches. Software needed to run the analysis includes a Hive working environment on top of Hadoop and MapReduce. Mount and R are useful for some additional statistical analysis. However, the focus of the project is on Hive. Hive's excellent for canned query applications and ad hoc customized searches, beneficial for forensic analysis. There are several resources available online to assist in installing these packages for anyone that doesn't already have them installed. Everyone should that's in the course, of course. Hadoop, MapReduce, and Hive can be downloaded from Hedera, and it has good instructions for installing that. The CRAN R project website is a good site for R to download and install that. And Mount can be downloaded at the GitHub location, and information is provided there as well. First, we create a log table on Hive, and this should look familiar to everybody in the class, so I won't cover this in detail, other than just to say that it does provide, through a serializer, deserializer, provided to Hive, the ability to parse server logs using regular expressions. Then we load the 7 server log data, and here we see the 7 logs were loaded correctly. Once the data are loaded, then we can start our discovery process for specific attack vectors. We're going to try to find patterns within the request field. This field shows the URL information for the resource or web page that was requested. Many attacks leave telltale fingerprints behind within this field that can be identified through the like operator using HQL. Following is an example. This example is called directory traversal and file inclusion. This kind of attack traverses the directory, usually at the root of the system, and also can call up executable files, .exe and .ini, for instance. And we see that we're using the like operator to find these terms, and the percent sign simply means to look for these terms regardless of what precedes or follows them. And notice that I am using the function lower. We have to convert everything to lowercase since the like operator for Hive is case sensitive, unlike most databases. The results are here, and we can see that there were several these are actual cases of attacks that were in that log file that fit this description. So we see lots of signs of file traversal here, in addition to the ubiquitous double dot, sort of Swiss Army enough of file traversal. We also see an INI file located somewhere in here. There's command.exe, so we do have some executable files in here as well. Command injection is another attack type. This type tries to disguise commands with HTML URL encoding. For example, ampersand comma, instead of putting a comma in there. 20 echo, 60 ID. These can be very hard to spot just by looking at a log file, especially when you have thousands or even millions of rows. Here's the result of that query, and we see a lot of HTML encoding here. Here's 60 ID, and you got 20 echo repeatedly throughout here, and very handy for spotting that kind of thing. Tracking and tallying failed request statuses. In addition to taking the direct approach, I just gave a couple examples. I have a number more in my paper, but in addition to taking the direct query approach, we can also track and tally failed request statuses. And I showed a variety of ways in my paper, but for the purposes of this demonstration, I'm going to show a time series example. Often an attacker may experience a number of failed attempts before hitting upon the right combination that brings success. And this pattern can be used to spot aberrations across the time where you have a higher ratio of failed requests to successes. Hosts with the most failed requests aren't necessarily attackers, but they can serve as a starting point for further investigation. Codes in the 100, 200, or 300 series range in the status field of a log file indicate successes. Codes in the 400 to 500 range are failures. This next bit of code, this HQL query, simply uses a case statement along with the substring command to locate. The substring command locates the very first digit in the status code of the 3-digit code. And if it's a 1, 2, or 3, it gives it a 0 and a new column. And if it's a 4 or 5, it gives it a 1. So it's easy to sort and identify those using this query. Next, we're going to do some time aggregations. And the time field looks like this in a server log. You've got day, month, and year, followed by hour, minute, and seconds, and then the time zone. We're going to focus for this demonstration on the day, the month, and the year. This query parses the day, month, and year, and there's a case statement that converts the alphabetic version of the month to a numeric version for easier sorting. And it also uses the substring function shown earlier against the time field. And we're able to parse it into several new columns as shown below here. You've got month, year, month, day, and year, month. There's one more I'd like to show, and that is year, month, day. And we'll do that with a subsequent view that calls this view here and concatenates some fields to give you year, month, day. Here we're going to generate the daily time series for failed requests. This is another view, and it calls the preceding view. And here you see the concatenate function, concat, where I'm concatenating the year with the month day as a new field called year, month, day. So now I can get a time series across years, multiple years, and across multiple months for days on a daily level. Once we have that view created, we can create 2 additional views. The first one will identify successful attempts, or failed attempts rather. The second view, successful attempts, and from those we can calculate a ratio. And you can see here that I'm identifying the status here, again, the substring status in 1, 2, or 3 for successes, and 4 and 5, the very first number in that 3-digit status code, as failed requests. Then we calculate the failed request ratio by day. So here we see, as a result of this query, that joins the 2 views together, 2 preceding views, and it creates a ratio, failed requests to successful requests, as a new column called fail ratio. And the time, a small sample of the time series is shown below. We've got the year, the month, the day, and then the ratio for each. Now we can export the data for further analysis. Here we just rerun the last query, but instead of running it as a standard select, we just put 2 lines above it, insert overwrite local directory, and then the location. Following that, we have the location where we want to put the file. And here's some R code just demonstrating what you can do with some of those results, the time series. And it'd be very difficult to get any kind of a time series out of that many server logs without a tool like Hive. Here we just import the data. And the column delimiter is actually one that is not visible with most tools unless you have an IDE that shows it. It is a caret and an A, and it's purposely done that way so that it can't be confused with a comma or a semicolon or other delimiter. R seems to handle it just fine, and you can also put in the separator field here, if you want, you can explicitly state it. Looks like that, and that will work. and put that in a variable called failed requests. And here we're adding some column names, date and failed request ratio. And then we're creating a standard deviation and an average. And from those two, we create a third variable that shows the average plus 2 times the standard deviation. And you can probably see where we're going with this. We're creating a control chart. And if you run this query, we'll identify any days that exceed 2 times the standard deviation above the mean in the fail ratio. And we've got 3 days that meet that criteria, that have higher than normal fail ratios. Actually, they don't look that high. We're using a standard data set peppered with a few cases of attacks. If this was a real log with an actual attack pattern with a sequence of events, you could very well see quite a large spike in that ratio. Now, the second part of the R code shown here just produces a plot, and this should be familiar to most of you. You can add lines to your standard R plot. This one adds a mean, a solid line. This one here adds a dotted line for the standard deviation, and we're adding a legend. And then we're saving it as a PDF file. Here we're creating a plot that uses a function called ACF plot, and that's from a package called FBasics, which in the preceding slide was shown up here. Library FBasics, Financial Basics is what that stands for. And that's so we can check for autocorrelation. Since it's a time series, I want to know if there's any seasonality or any kinds of aberrations where the trend is essentially correlated to itself, any kind of cyclical behavior or anything like that. And so we run a plot on that as well. So here's the control chart, and we can see that there are 3 days that indeed exceed that dotted line, which is 2 standard deviations above the mean. The mean is given by the solid line. Not any really huge spikes, but we see a few there. And we also see that there's no evidence of seasonality. The only significant bar, which is given by the bar that exceeds this double line that indicates statistical significance, it occurs at the 0 lag point here on the x-axis. So there is no lag that we have to be concerned with in terms of the trend being correlated to itself. So it's essentially not really seasonal. Doesn't seem to be any aberrations there. So it looks like it's okay to analyze. And this control chart should be pretty valid. We can also produce other analytical data sets with Hive, such as a logistic regression in MOUT, which is what I experimented with here. Here I exported the previous view, which was called status groupings, you may remember, which groups the status by type, either failed or successful, stored it in a location. Then to import it into Mayhout, you've got to replace that delimiter. Unfortunately, what may work great for R doesn't necessarily work for MOUT, so you have to replace that with a comma. You can do that with awk software or SED or an editor like Emacs or V, which is what I did. And once you've done that, you can specify your model. The predictor in this case I just specified as host. I've tried many other things, but this one looked interesting to me. And we're predicting the failed access, trying to see if any hosts are associated with failed accesses. And it produces a long list of results, as you would expect. There are many hosts. But if you plot the coefficients for each of the hosts in a chart, it shows that the way this is set up, the negative coefficient shows hosts that are prone to successful requests. The positive would be unsuccessful. So we don't see a real strong pattern on the unsuccessful side, not nearly so much so as the successful side. If there was an actual attack sequence that was loaded in the data, I would probably expect to see something much more pronounced there. So it's not too surprising given that it's Amazon sample data. In conclusion, Hive provides a very useful framework for analyzing large amounts of server log data. It's flexible, allows drill downs, and it can also be useful for having a collection of queries and methods to analyze common vectors of attack. This isn't a comprehensive list of potential attacks, but it's hoped that the ideas offered here may serve as a catalyst for further discussion and research into this topic.